In these problems, we're going to start applying one of the rules for taking derivatives of functions. And when you take a first-year calculus course, derivatives are usually half of it, and the other half is integrals. It's kind of one of the main concepts in a calculus course. So before we start applying this rule, which is the power rule, we should talk a minute about what a derivative actually is, because it's good to know what you're doing. The rules are easy enough to remember. It just takes a little bit of practice. But knowing why you're taking a derivative and what it actually means, that's very important. And what a derivative is, it's really the rate of change of a function. So let's look at a function f of x equals x squared. So at different points at this function, its rate of change is different because it's a curve. So for example, if you had a straight line, so let's just say y equals x, the rate of change is the slope of that line. As x goes one square over, y goes one square up, x goes one square over, y goes one square up. That's the rate of change, and it's 1. The slope is 1. So for a straight line, the slope is its rate of change, and that is actually the derivative. For a figure like this, f of x equals x squared, you can find different rates of change along the curve. So for example, from 0 to 1, 1, those are both 0, 0 to 1, 1. Those are both points on the graph. X goes over 1, y goes up 1. So that's a rate of change of 1. The slope is 1 there. If you went up to out to x equals 2, you're suddenly up at 4. So at that point, x went over 2, y goes up 4. It looks like your rate of change is 2. And as you go further up the curve, it gets steeper and steeper. Now we represent that, the rate of change or the slope of a curve, by drawing lines that are tangent to the curve. So in this drawing, I have f of x equals x squared, and you can see here at the point 1, we've got a line that's tangent to the curve. It just touches that curve. And what you'll notice is that the slope is 2. So when x equals 1, the slope is 2. This other line I've got here is tangent to, just touches the curve barely at x equals 2. And the slope of this line is actually 4. So at x equals 2, the slope is 4. And if you went on up here, if you went up to, let's say, 3, and you drew a tangent, you'd find that the slope would be 6. And you have this relationship where the slope is always 2 times the value of x. That is the derivative of this function of x squared. So that's one way to think about it. It's important to remember that the derivative is finding the rate of change of something, and it can be represented by these tangent lines, the slopes of these tangent lines to the graphs. There are other interpretations of what the derivative is, and we'll come across some of those as we go on. For right now, we're going to be working with taking derivatives of polynomials. So x raised to certain powers and constants multiplied by it. The rule here is called the power rule. And what you're going to do is you're going to take the power and bring it down in front as a constant and multiply x by that power. Then you're going to subtract 1 from the power. So for example, if we did our f of x equals x squared, I would bring that out in front as a constant, so I'd have 2. Then I'd take this x squared and subtract 1 from the power, so that would be x to the first, which we'd just write 2x. So the derivative would be 2x. And one of the things about derivatives in calculus is that there's some competing notations. I'm going to use the df dx. And what that represents is the change in the function with respect to the change in x. So how fast is the function changing with respect to how fast x is changing? All right, let's try applying the power rule here. So f of x is 8x to the 4th minus 9x to the 9th. df dx, or the derivative of f of x, is going to be, well, let's see, we take the power and bring it down as a constant. And I've got an 8 out there, so I'm going to have to multiply the 4 times the 8. So 4 times 8 is 32. And then I just subtract 1 from the power. So this is going to be x to the third. And I do the same bit with this piece here. So 9, bring it out in front as a constant. 9 times 9 is 81. And subtract 1 from the power. So our answer there is the derivative of f of x is 32x to the third minus 81x to the eighth. All right, let's try another one. Here we have the function f of x is 4x to the 5/8. So I have to bring the 5/8 down as a constant and multiply it by the 4. So I'll write that like this, 5/8 times 4, and x now is going to be to the 5/8 minus 1. Well, 5/8 minus 1, that's 5/8 minus 8/8, that's negative 3/8. So this becomes x to the negative 3/8 power. And then we can do our simplifying. Let's see, 5 times 4 is 20 divided by 8. I think that's going to be 5 halves times x to the negative 3/8. All right, one more. So we've got 2x to the 6th. I'll bring that 6 down and multiply it by the 2. I get 12. And x, instead of to the 6th, would be x to the 5th. And then we've got a negative 3 times x. So you can think of the power here being 1. 1 times negative 3 is just going to be negative 3 still. And then x is going to be to the 1 minus 1, or to the 0 power. And x to the 0 power is 1. So this is really 3 times 1. So the x just goes poof, and you're left with the constant. And then we have x to the negative third. So I'm going to bring this down as a constant. So actually that's going to be a minus 3x. And then I have to subtract 1 from the power. So that becomes x to the negative 4 power. So that's df dx. So that's a little bit of work applying the power rule to take derivatives of polynomials. My name is Larry. I'm a teacher at EdVision's off campus. It's an online project-based school in Minnesota. If you're interested, you can check us out on the web at lovethischool.org. Thanks.